I want to talk about the tangent line problem in a little bit more depth and talk about the results that we get with the tangent line problem. So the slopes that we get, how we can apply that, and what those mean in terms of different types of problems. Before we do that, just a couple of refreshers. First of all, the slope formula. Hopefully, this is something that you're familiar with. I am going to be using this delta notation here quite a bit. So remember, delta means change. So delta y means a change in y, or to find a change in a variable, we subtract them. So delta y means we're subtracting y values. Delta t would mean we're subtracting time values. These are hopefully terms that you remember from geometry class talking about circles. They don't just apply to circles. We can use these terms with any kind of curve or function. So a secant line is going to be a line that goes through 2 points on a function. Remember that we're going to be talking about slopes here. So with a secant line, it's easy to find a slope. We just take the coordinates of those 2 points and we plug it into the slope formula and we get a slope. Tangent lines are really where the interesting things happen. So a tangent line is going to be a line that essentially has the same slope as the curve at what's called the point of tangency here. And a myth about tangent lines is that it touches the curve and doesn't intersect it again at another point or doesn't go through. A lot of times tangent lines don't go through the curve, but it could. It can intersect the curve again, so we could get a graph that looks something like this. So this blue line here is not only a tangent line, but it would also be called a secant line because it's intersecting twice. So it could be both. What we're going to be looking for, though, with the tangent line problem is what the slope of that line is. Remember when we tried finding slopes with just a single point, though, we get 0 divided by 0, which is indeterminate. We don't know what that is. And so that's where new calculus methods are going to come into play. So tangent line problem, we have a function, we have a curve. We want to find the slope of a tangent line. And again, just having the single point is where the trouble is going to come in, and we're going to have to come up with methods. And I introduced that with Jordan Hicks throwing a fastball and taking information that we knew about the fastball, the time that he released it, the time that the catcher caught it, and then we got into a little bit more depth, but using what we knew to find the slope of a graph of the position of the baseball. And what I want to emphasize here is that when we did this and we included units on our numerical values, we got units that were in feet per second originally, and then ultimately miles per hour after we converted, which told us that that's how fast the ball was going. I do want to point out here that this is actually the slope of a secant line. So it tells us on average during the course of the pitch how fast the ball was going. But the important thing is I want to know how we interpret a slope in a coordinate plane like this in the context of a problem. So the miles per hour there is a clue that we're talking about how fast the ball's going. If we look at some other applications, let's say we have a company that's producing thingamajigs, and this graph here tells us how much it costs that company to produce a certain number of thingamajigs. We have, this one's a straight line, so this is going to be nice and easy to work with. So if we produce 0 thingamajigs, it costs $1. If we produce 3 thingamajigs, it costs $7. And we have a nice linear relationship here. So if we were to find a slope in this coordinate plane, the slope would be a change in cost divided by a change in the number of thingamajigs. And in this problem, that slope is going to be 2. But if we throw in units here, that's going to be $2 divided by thingamajigs. So by including units in the change, the vertical change and the horizontal change, then we get units here that tell us how we interpret that slope, how we interpret that 2. In this case, $2 per thingamajig is telling us that for every thingamajig we produce, it costs us $2 more. Another example here might be a tank of water that has 800 gallons in it at t equals 0, at t equals 8. It's completely drained. And we can see at different points along the way how much water is in there. Slope in this case would be a change in the volume divided by the change in time. and we get a slope of negative 100. But if we include units on volume, we have gallons. And if we include units on time, we have minutes. So this slope of negative 100 tells us that there's 100 gallons draining from this tank every minute. And that's consistent. It is a line here, so every minute it's 100 gallons being drained. Where things get interesting is when we have curved graphs like this. So let's say we have a population of bacteria growing in a petri dish, and we're modeling how many bacteria are in the petri dish after a certain number of days. We might get a graph that looks like this. We wouldn't expect that population graph to be a line, linear. So first of all, if we're going to find a slope in this coordinate plane, I don't know what that slope is. We could talk about slopes of secant lines or slopes of tangent lines, but regardless, when we have a vertical change, we're talking about number of bacteria. And when we have a horizontal change, we're talking about days. So we would interpret whatever slope we get as a number of bacteria per day. So that tells us how fast the population is changing. If we want to know how fast the population is changing at different points in time, then we would want to look at tangent lines. So at the beginning, on the first day, when we're just starting, this tangent line right here and the slope of that tangent line would tell us how fast the population is growing at the beginning. This one, we can use another point here on the tangent line at 200 and get a slope of 50. But remember, our units are bacteria per day. So let me, sorry, I'm going to rewrite all this. I want to clarify here that I'm finding the slope at t equals 0, and that's going to be 50 bacteria per day. And the interesting thing here is that over the first day, there's not 50 bacteria being added to the population. That would correspond to this point right here on the tangent line, but the population is actually bigger than that. It's more than 150 after the first day. So what this is called here is an instantaneous rate of change. So at t equals 0, the population is growing by 50 bacteria per day. However, as time goes on, even during that first day, the rate of growth is actually going to be going faster. We saw this sort of thing happen with Jordan's fastball, where he released it. It was going 105 miles per hour, but the air resistance slowed it down to about 93 miles per hour by the time Yadi caught it. So we have a rate of change here that's changing. We could find the slope at t equals 3. I'm going to approximate this slope here because I don't know for sure that it's going through this point, but this tangent line right here, we could find the slope just using another point that looks like it's on it. And that looks like it's going to be about 224 bacteria per day. And so as we might expect here, especially looking at the graph and the slope of our curve is getting steeper, is getting bigger, that as time goes on, the rate that the population is growing is getting faster. So at the beginning of the third day, now the growth is increasing. So it's increasing by 224 bacteria per day. And even over the course of the third day, that's going to be going up. So I want to wrap this up by talking about how we might approximate this using some methods that are going to lead into what we're going to do with calculus. So again, if I just want to find the slope of a tangent line and I have that single point, I plug in that point twice, I end up getting 0 over 0. That's indeterminate. We can't figure that out. So one way to approximate this, besides just going off and looking for a point that looks like something that we could approximate, we could choose 2 points, but we could choose 2 points so that the secant line through those 2 points is going to be close to the same thing as the tangent line through this point. And what we did with Jordan's fastball is we chose the point of tangency, and then we chose another point off to the side, and we found the slope of that secant line. All right, that's one option. But if we do that, we can see that this slope is going to be smaller than it should be. If I go to the right, the slope is going to be bigger than it should be. So rather than doing that, I'm going to choose 2 points on either side. So this is a pretty common method here. So I move a little bit to the left and plug that into my function, and move a little bit to the right, plug that into my function, and use those 2 points to find the slope. And if I do that, I'm going to get a slope that's really close to the slope of the tangent line. So the slope of that is going to be about 224 point. Sorry about that. About 224.178 bacteria per day. And that's the slope of the secant line using these 2 points at 2.9 and 3.1. So what I did is I just moved a little bit to the left, move a little bit to the right, and used those 2 points. Now, the actual slope of the tangent line here is 224.084 bacteria per day. You can see that this answer is really close. The approximation here is really close. It is a little bit off, but it's a pretty good approximation. And as you might guess, we could make this better by, instead of going from 2.9, so I'm going to say t is in the interval from 2.9 to 3.1, we could make it better by going from, say, 2.99 to 3.01. And the slope of the 2 points going through these 2 times is going to be even closer to the slope of the tangent line. We can make it even more accurate by choosing points that are even closer. I never will be able to get an exact answer, but I can always make my approximation a little bit better by using this. I do want to mention one more thing here, because this is a symbol that you're probably not familiar with. It's a Greek letter epsilon, which essentially just means it's in. So it's in the set or in the interval from 2.99 to 3.01. We'll come back to this idea after we spend some time talking about limits, and we're going to talk about how we can go from this approximation method here to making our answer exact.